Welcome everyone. It's a great pleasure to have Vijay give the second talk in 2 weeks. I just did an introduction last week. I don't think I need to repeat it. So without further ado, over to Vijay, talk about perfect matchings in planar graphs.
Yeah. Thank you so much, Nikhil, for this very kind invitation to a wonderful place. And thank you all for coming. So this is a very recent result showing that finding a planar graph perfect matching, this question is in NC, the class NC. So I'll give you all the definitions real fast, but I'm sure everybody here is familiar with them anyway. So a set of edges, subset of the edges of a graph such that there's exactly one incident at each vertex, such as these red edges. Exactly one is incident at each of the vertices, 6 vertices, 3 edges. It's called a perfect matching. And there are 3 kinds of problems that arise with this problem. So the matching problem is really holds a very, very distinguished position in the theory of algorithms because in attacking this matching problem from these various viewpoints, which I'm coming to, the theory of algorithms got some of its biggest tools and ideas and techniques and complexity classes and ways of doing things. So I'll go over some of these as we go along. So there are these 3 problems about algorithmic problems about matching. One is the decision problem. Does there exist a perfect matching in the given graph? That's polynomial time solvable. Search problem is output of perfect matching. If there's one, that's also polynomial time solvable. These were the works of Jack Edmonds in '65. And in giving these algorithms, he also defined the class polynomial time for us and showed it. In that same paper, he gave a philosophical note saying why it's so important to look for polynomial time algorithms. And then there's a problem of counting the number of perfect matchings in a given graph, and that's sharply complete, which is worse than NP hard. And this was proven by Les Valiant, and in proving that it's sharply complete, so in other words, counting the number of perfect matchings in a graph is exactly as hard as counting the number of satisfying truth assignments to a SAT formula, which is already an NP hard problem, right? So in showing this, Les Valiant, who showed this, he defined the class sharp P for us, for all of algorithms. So these are 3 algorithmic problems that we'll be coming to fairly often in this talk. And in particular, I'll be talking about fast parallel algorithms, very fast parallel algorithms. So here are these 2 classes, NC and random NC. In NC, you have a polynomial number of processors, but each one can run for only a polylog amount of time. So any one of the processors cannot even see the entire input, which is polynomial in n being the number of vertices. So the input is polynomial in n long. But these processors talk through a shared memory, so they can different processors can see different parts of the graph and then do whatever, through the shared memory. And if you can solve this in the problem of finding a perfect matching in this kind of a complexity class, then it's said to be in NC. And this is sort of the maximal parallelism that you can get in a problem. And this class has extremely, there are some classes for which when you get an algorithm, you have to go very deep into its structure, its natural combinatorial structure. And that has been the case for NC. Whenever people have found NC algorithms, it has involved very beautiful, deep structure, canonical structure. So sometimes when you cannot really get a deterministic NC algorithm, you allow the processors to flip coin, and then it's called random NC, and you want the output to be coming out with high probability. Sometimes I'll call these professors, but that's just my out of a mistake. Okay, think of them as processors, really. Okay, so let's talk about, I just gave you the summary with respect to polynomial time, with respect to sequential algorithms of the three algorithmic problems. But here's the summary with respect to parallel algorithms. So the decision problem of checking if a given graph has a perfect matching is in random NC, but not known to be in deterministic NC. And this goes back to a very old result of Lovaas, a very fundamental paper, where he doesn't talk about parallel algorithms at all. But what he did in that paper was he gave a completely different way of solving matching problems algorithmically than was done before. The algorithms before were combinatorial, paths, trees, and flowers, blossoms, and so on and so forth. And he showed a completely different way of approaching the problem through the Tut matrix, through linear algebra, and randomization, polynomial identity testing. So a beautiful paper, and at the anybody who reads the paper can see, okay, this gives an RNC algorithm for the decision problem. So that's why I'm attributed to Lovaas. And but the problem of finding perfect matching was open for a very long time, and it was solved by Karp, Uffel, and Wigderson, who gave a random NC algorithm. And soon after, a different random NC algorithm was given, a simpler one by Mulmule, Umesh Wazirani, and me. And so once again, studying matching from the parallel perspective has also yielded beautiful insights. Here, these people also went on to giving a relationship between search and decision problems, especially with respect to parallel algorithms, and that has been very important insight for us, how are search and decision problems related complexity-wise. And this work gave us isolation lemma, which went on to finding many applications. It's a fairly key probabilistic lemma. And that's where the story stopped on arbitrary graphs and parallel algorithms. What was left over after this story was, is matching is an NC? Can you remove the randomization? And that has remained with us for all these years, and God knows how long it'll take. But every now and then there's some insights on that. And recently, really some very beautiful insights due to Fenner, Gurjar, and Therov. Sorry for the pronunciation. So they showed how to find perfect matchings in bipartite graphs in quasi-NC. So in quasi-NC, the time is still polylog, but the number of processors is not polynomial, but 2 to the polylog n. So not exponential, but somewhere between polynomial and exponential. And this took a fair number of ideas. In particular, they end up de-randomizing isolation lemma partially. Can you do it fully? I particularly doubt it, but I wouldn't have guessed this result either. And then there was a very nice result extending this to general graphs by 2 authors who are here in this audience, Svensson, Ola, and Yakov Tarnowski. And they really did quite amazing things. This was already a very fine piece of work, but then they had to delve into deep properties of odd cuts and the perfect matching polyhedron to get to this this result. In fact, it was a Fox Best Paper Award last year. So that these quasi-NC algorithms, they didn't answer the whole question, but they gave us some very important ideas. In particular, our work mostly indirectly, maybe a little bit directly, used these ideas and some other ideas that I'm going to come to. But before coming to the other ideas, let me say why it is, what happens in the case of planar graphs with respect to these 3 problems, decision, search, and counting. Okay, so in general graphs, basically, as I just told you, decision is in RNC and quasi-NC, search is in RNC and quasi-NC, counting is sharply hard. There's nothing more to do in parallel. It is hard, period. Okay. What happens for planar graphs? Well, decision is in NC, counting is in NC, believe it or not. What was here, sharply complete, is in NC. But search was not known to be in NC for 30 years. That was a big anomaly. And why is counting in NC? So there was a work of a physicist, crystal physics researcher named Castellan, very important researcher, who was studying arrangements of well, minimum energy states, and he had to count the number of perfect matchings in a planar graph, and he found a polynomial time algorithm outside of CS, a physicist. And then one can sort of put together that this will get to an NC algorithm, but the place that it was done was in a paper of mine where I did not only this, but also for K333 graphs, so graphs that do not have a K33 minor. That's a superclass of planar graphs. And we'll come to this result towards the end of the talk. But in any case, the problem is this question mark. How do we reconcile with this unbelievable story that decision and counting are both in NC, and search is nowhere to be found here? The best we can do is random NC, which is the same as for arbitrary graphs. Okay. Now, if you take the special case of bipartite planar graphs, so think of special case of special case, then it's an NC. And this was found by Miller and Naor in '95 through flow means, using flow techniques, and by Mahajan and Varadarajan. Through a different technique, they actually use this fact that counting is an NC. And I'll go over their algorithms because those are some key ideas for our work. And we follow along their path further to take care of all planar graphs. Okay, so this is our main result, of course, that there's an NC algorithm for finding a perfect matching in planar graphs. Okay, so why are these? What happens? How does this anomaly arise? And in particular, how does counting become in NC for planar graphs? So here's a short synopsis of why that happens. So let's look at first a bipartite planar graph, which will have n vertices on each side. And so there's a row for each vertex on the u side and a column for each vertex on the v side. And the ijth entry is 1 if ui vj is an edge. Okay, like that, and 0 otherwise. Now, the number of perfect matchings in this graph is the permanent of this matrix, which is known to be hard to compute. But we are dealing with the bipartite planar graph, so can there be something better to be done? Well, let's wait and see. In general, permanent is hard. But what can be easily computed is the determinant of this matrix, where you also have a sign term depending on the permutation that you picked here. And that is easy to compute, the determinant. But then, of course, different perfect matchings can have different signs, and so they can kill each other, and the determinant could be nowhere close to the number of perfect matchings, maybe even 0, okay, or negative. So at this point, we recall a very nice idea due to Polya. He said, take this matrix A, and how about changing some of these plus ones to minus ones to get a matrix A tilde in such a way that the determinant of A tilde equals the permanent of A. Can you even do that? Is there even an A tilde like that? Okay, and sometimes you can do that. But the big place where this idea bears fruit is when you go to arbitrary planar graphs and look at non-bipartite planar graphs and look at the adjacency matrix, which will be symmetric now. So each edge has two ones on it, the ijth entry and the jith entry, and just arbitrarily make one of these plus one and the other one minus one. Okay, so you got the adjacency matrix, and you just arbitrarily changed one entry to one of these two to plus one, one to minus one. That gave you a skew symmetric matrix. Of course, you have 0 down the diagonal. What happens now is that the determinant of this matrix is the sum over all perfect matchings of some sign term for each perfect matching, depending on those two and which ones you made plus one and minus one, and what's the sign of this permutation. Okay, so it's the square of this thing. And now we can ask the same question again. Can you fix this, how you assign plus ones and minus ones, so that all of these perfect matchings have the same sign, either all plus one or all minus one? Okay, and of course we are in some sense orienting this edge. Let's say that we orient it from I to j if ij is plus one and ji is minus one. Okay, so we have oriented the whole graph, and that tells us how to put plus and minus ones here. And Castellan's big observation was that you can do this, find these signs for planar graphs in polynomial time, so that in fact the determinant of this matrix is the square of the number of perfect matchings in the graph. Okay, and then determinant can be found in NC, and this thing is called a Pfaffian orientation. The one that works can also be found in NC. So you got in NC the fact that you can find the number of perfect matchings in a graph. Okay, so that's the end of that mystery, I hope, in a nutshell. Question? No. Okay. So how are we going to use this fact? How are we going to use the fact that counting can be done to do search of a perfect matching? So for this, we have to go first to this beautiful idea of Mahajan and Varadarajan for planar graphs. And they have basically a two-step algorithm. Find a point x inside the matching polytope, and iteratively move this point to lower and lower dimension faces until you reach a vertex of this polytope, which will be a perfect matching. Okay, so you start inside in the interior of this polytope, and you move, say, to this face, which is lower dimensional, and then to this face, which is lower dimensional, and then to this face, which is dimension 0, and is a perfect matching. But how do you move? How do you find this point x? So the starting point involves the fact that you can find the number of perfect matchings in the graph, which is the denominator here. And you can also find the number of perfect matchings involving E, or actually the number of perfect matchings not involving E, because you remove E from the graph and find the number of perfect matchings. That's the number of perfect matchings not involving E. Then you subtract and you get this thing. And you do this for every edge in parallel. So you get these numbers x's, and you get this entire vector that sits right here, because this is the convex combination of all perfect matchings. This thing, which is where the numerator is the number of perfect matchings in which E participates, divided by the total number of perfect matchings, is exactly the convex combination with equal weight to all perfect matchings of all the perfect matchings. So it sits right in the middle, in the interior of this polytope. Okay, so how do we accomplish the second step now of moving to lower dimensional faces? So for that, let's look at the perfect matching polytope. And how does that go? Very simple. You have, of course, a variable for each edge. And at each vertex, the xe's sum up to 1. Integrally, it's saying that exactly one edge should be incident at this vertex from the perfect matching. And of course, you have non-negativity. So let's say that this is our planar graph Okay. Now here, let's find a cycle. And lo and behold, it will be even length. You see why? Yeah, it's bipartite, right? So yeah, just making sure. Yeah? And it's even length. Now we got this x vector already from the previous slide. So what I do now is subtract a small epsilon from this x vector xe, add a small epsilon, subtract a small epsilon, add a small epsilon, and because this cycle is even, I'll have alternately as many minuses as pluses. And in particular, at these vertices, there's no change in the total. So that thing is retained. These vertices are still tight, right? What's happening is that these things are moving towards 1, and these things are moving towards 0. So just do enough change that either one of these hits a 0 or one of these hits a 1. If it hits a 0, you remove this edge. If it hits a 1, you match this edge off and remove all the other incident edges. And you have brought down to 0 at least one edge. And you're still inside the polytope, right? So you have satisfied at least one more of these inequalities with equality. That's why you're in a lower dimensional phase.
So which ones are plus, which ones are minus is arbitrary?
No, arbitrary, yeah. Take any edge and start from there. Yeah. And so you got basically you reduce the dimension by at least 1 of the point x, the face on which it lies, right? Only 1, huh? How do we do more? Because if you do this sequentially, that will take us well, too much time. So what we can do is, if we take many cycles which are edge disjoint, then we can do the same rotation independently in all these cycles, because they are edge disjoint, and at these vertices, of course, no change happens. They are still tight, and each of these cycles will lose at least one edge. So if you manage to find lots of edge disjoint cycles, you get lots of decrease in dimension. So how many edge disjoint cycles can you find? Well, what you do, okay, we'll come to that. Okay, so that's what you do, and it turns out that you can find omega n edge disjoint cycles, omega of n. I'll see a quick reason. Okay, and that means that you lose a constant fraction of the edges, because you had order n edges because it's a planar graph, and you lost omega n edges. So, okay, so you remove these edges that disappeared, clean up and repeat, and then of course in a log number of iterations you're all done, because you're decreasing by constant factor the size of the leftover graph. Okay, so how do we find this? Of course, remains as a question to be answered. How to find omega n edge disjoint cycles? Okay, so we'll come and answer it, but let's see. This is the same thing that we want to pursue in non-bipartite graphs. Okay, but the problem is that now the matching polytope is much more involved. In particular, it has exponentially many constraints of this kind. So for every odd set S, you have that the number of edges crossing the odd set, such as this odd set, which has odd number of vertices inside, then the XEs on these edges that cross S, that are in the cut of S, should be at least 1. Why? Because any perfect matching has to pick at least one edge going through this cut, because there are only an odd number of vertices inside, so one of them will remain unmatched through the edges inside, so it has to be matched outside. So fractionally, the same thing will happen. You'll have to have at least one edge in the cut, right? And there are exponentially many such constraints. Okay, how do they influence things? How do they influence things is that because of these constraints, you cannot rotate a cycle. Okay, for instance, you cannot necessarily rotate a cycle. So if we take this cycle, so this is this all 1/3 is a point inside the polytope. Now, if we take this cycle and subtract, add, then what happens to this cut, which was initially at 1/3 plus 1/3 plus 1/3 was exactly tight, goes under tight, and so this inequality becomes infeasible. You're outside the polytope. So you're at an infeasible point already. So the whole game is finished. Okay. So obviously, we are not going to be able to rotate every possible cycle however we want. We get blocked by these odd cuts. So how do we repair this thing? Well, simple observation. If we shrink this S into one vertex, then this graph has a perfect matching. Find a perfect matching. Maybe it's this and then this edge. So one of these edges will match something inside here. So if we match this edge, then this guy got matched, and then we match these two. If we match this from outside, then we match this thing inside, right? So once we find a matching here in this shrunk graph, then we open up S and forget about the matched vertex inside, and then we find a matching inside S, and we are done, right? So yes, we didn't manage to rotate that cycle and lose an edge, but we managed to get to a smaller problem, because once we shrink S, we have shrunk at least one edge. So this is a smaller problem. I think I need some. Yes. Yes. Okay. Yeah, my mistake was I didn't ask you for the idea here. So next time I'll ask you for the idea, because yeah. Okay. So how do you deal with the fact that you cannot rotate this cycle? The reason is that this cycle is crossing an odd tight cut, which was already a cut that was already tight. If it is already tight, shrink that cut. Shrink that odd set. What happened is that you lost at least one edge, because there must be at least one edge that's entirely inside S. So the remaining graph has at least one less edge. So you get to a smaller graph. We were getting rid of single edges. Remember, at first, we got rid of single edge. And we got to a smaller graph. Find a perfect matching here. Okay? And then that matching will match this vertex outside. And you see where this vertex really is incident inside S. That vertex is matched. Throw it away. And find a perfect matching in the remaining S. So we got two smaller problems, definitely smaller. And that was our goal, right, to decrease the size. For now, just by one edge, but we'll get to more decrease. Yeah?
The latter does not have a perfect matching like the former does, right?
No.
If the perfect matching was not assigning an edge inside S, suppose that you had this triangle and then you had isolated edges.
No. I'm saying that if this is a tight set,
I see.
then you will have
still a fractional sum.
Yeah, then you will have a perfect matching in the shrunk graph. No question about it. Okay. So yeah, do, because this is like, this is a very important. It's not just a brick, but it's a whole slab that we are going to build many things on. So yeah.
So how do you pick the vertex that you actually match to outside, inside?
It doesn't matter. Look, I mean, here, if you match this edge, that's saying this edge is matched, I'll match this edge. If you tell me match this edge, meaning this edge, then I'll match this inside. If you match this edge, then I'll match this thing inside. No matter.
So the exterior one might have multiple neighbors inside.
How?
So if that, if the onset.
So it doesn't matter which edge you pick. Just pick one edge,
Okay.
match it off. Inside you will get an even number. So this thing is matching critical. You throw out any vertex, the rest of it has a perfect matching.
Yes.
Okay. Yeah.
So there might be a subtle thing. So if there's an edge on the tight cut, if the value is 0, then you shouldn't add it to the new graph, right?
I'm assuming that every edge is in some perfect matching.
Okay, yeah, sure.
Because that I can guarantee, because I have an oracle for a number of perfect matchings, I can already prune out edges that are not
Fine.
any perfect matching. Sorry.
Okay, yeah.
I was assuming that you're right. I should have mentioned it.
I think this, then there's no conflict.
Then there's no problem, right? Okay. Good. Right? Okay, so then we are all set, and I see that everybody's happy now. Okay. Okay. So this is a small progress, but we have to do a lot of progress of this kind, moreover in parallel. So basically, I think I told you all of this stuff. Okay. So now, of course, the big challenge is how to get a lot of progress. So either remove lots of edges or shrink lots of edges, all in polylog time in one iteration, right? So this is the part that I'm going to deal with: how to move inside the polytope and decrease the dimension a lot. And at this point, I will pick up the question that I left behind, namely how to find lots of omega and edge disjoint faces first in bipartite graphs, the idea of Mahajan and Varadarajan. And that's very simple. The point is that once you clean up the planar graph, once you make sure that no face has more than 12 edges, and those big faces you can deal with later, okay? So without loss of generality now, let's assume every face has at most 12 edges. Then you take any planar embedding and look at each face as a cycle. It's an even cycle. And so it turns out you have omega n faces, and now using Luby's algorithm, you can find faces that are independent. They do not share any edges. Maximal independent set of faces. And that will also be omega n. And so we are done. Right? Was it too fast or? Basically, huh?
That was a bit fast.
Bit fast. Okay. So assume without loss of generality, because of this cleanup, that all faces are small. They involve less than 12 edges. If so, there are omega n faces in the planar embedding. Okay. Each face is only at strictly less than 12 edges. Now, any one of these faces is good to be a cycle, but we want edge disjoint cycles. So let's say that two faces interact if they share an edge. Okay, if so, put an edge. So put a vertex for each face, put an edge if they share an edge. And now in this dual graph, find a maximal independent set. That can be done in NC. And that will give you a bunch of faces that are edge disjoint. And there'll be omega n because each face was small. And so no face excludes too many, right? Throws out too many others. And so we get omega n faces in parallel. And we can do that trick of rotating all of them in each cycle in parallel. So we got a substantial reduction in dimension in parallel, and we can do it all in log n iterations. Yeah.
Provided you don't have any of those onset constraints.
Sorry, no, bipartite.
Oh, this is bipartite. Yeah.
Yeah. No, I know that their algorithm extends to non-bipartite graphs that don't have offset constraints, but that's not. Yeah. Okay. So, what if faces are odd? This was your question, right? So, what if faces are odd? Then you may not be able to get lots of even faces. Maybe, for instance, here you get only odd faces. Okay, but if you get these two odd faces, then you can find a path. In this case, there's just an edge between these two, between a vertex in this face and a vertex in this face, and you can get this walk, which is even length. And again, do the same trick: plus, minus, plus, minus, plus, minus, plus, minus. So this edge gets two minuses. Fine. But if you do this plus minus, then every vertex is happy because it got 2 plus epsilons and one of minus 2 epsilon. So this vertex is still tight, and these edges are trying to go to 0. These edges are trying to go to 1. Again, we can do enough rotation till one of those things happens, unless we get blocked by an odd-set constraint, right? But the first thing at least has been accomplished, because again we have omega n faces. Again, we can find independent ones that are even, plus pairs that a pair of odd ones, find paths between them, and so we get omega n walks that are edge disjoint, right? So instead of omega n cycles, we got omega n walks, but I'll just call them cycles just to keep life easy. Okay, so that can be done, and the rotation may not be doable because of what Nikhil said. So that's the big thing we have to attack. Yeah.
How do you detect that you are blocked by an odd-set constraint?
How do you detect? Good question. Good question. How do you think you would detect it? The only way I know right now is through binary search. But we won't have to answer this question, fortunately. Okay. It's a very good question. Yeah. But fortunately, we'll bypass this altogether. Okay. Okay. So what is it about bipartite graphs that makes you independently deal with all these cycles that are edge disjoint? Basically, if you move on this cycle, one cycle, you go to this face. If you move on the other cycle, you go to that face. If they are edge disjoint, you can move on both cycles and go to an even smaller dimension face. In non-bipartite graphs, what happens is you rotate on one cycle, you go to this face, you rotate on that cycle, you go to the other face, you rotate on both cycles, and you come out of the polytope because you violated an odd-set constraint, and that was giving you this hyperplane. Okay, and here's an example. You rotate this cycle, and this odd-set becomes tight. Okay. Oh, sorry. Maybe you rotate this. Yeah, you can rotate this cycle by epsilon1. You can rotate this by epsilon2. You rotate both, and this odd set became under tight, infeasible, right? And we don't even need to detect it. So, I mean, it's all a matter of heavily surreptitious stuff at this point. Okay. The big idea is now. Okay, and the big idea is you have these omega n walks that you want to rotate in parallel, this one by epsilon1, this one by epsilon2, this one by epsilon3, and so on, so that each walk, you want to find this, what are these epsilon1 through epsilon omega n, so that each walk either loses an edge or hits a tight odd set. And this walk may hit a tight odd set, which is not necessarily its own private tight odd set, because the tight odd set may also have other walks going through it. And so the epsilons of those walks come into the picture when this tight odd set goes tight. This odd set goes tight, right? So it's a highly constrained question of how to find these epsilon1 through epsilon omega n, so that every cycle gets blocked one way or the other by losing an edge or hitting a tight odd set. How do we do that? Do we solve an LP? Of course, the epsilons are all have to be positive, right? Because we chose a direction and we are going to move it like this. Do we solve an LP? But LP is not an NC, and even if we did, I don't see how to do it with an LP. Sounds like a heavy linear algebra problem of some kind, right? Suddenly you want to satisfy all these equalities, right? Either this goes to 0 or this thing adds up to 1, or God knows how to do that. But here's an idea. So this is really the key idea of the whole work. And hopefully it has other applications later in some situations. So basically, what we want to do is we want to arrive at a face. So let's look at from the upper, a little bit higher abstraction. At this point, we want to arrive at a face where suddenly all cycles are blocked. Okay, so that no more rotations are possible. either because the cycle has lost an edge or because the cycle is hitting a tight offset, and that's the reason that you hit this face. Okay, so our idea for doing this is the following. We choose a weight vector judiciously, okay, and find a minimizer of w dot x in the polytope, and the minimizer will obviously go and hit a face, right? Because if you minimize it anymore, you'll go outside the polytope. And what do we require from each cycle? We want that w dot x should decrease as you rotate along the cycle. Okay, so that if you are at this face, you have maximally rotated it. You cannot rotate it anymore, because if you rotate it anymore, one of those two infeasibilities will happen. Either something will go negative, or too positive, or under tight. Right? So basically, each cycle has been maximally rotated, and the reason for that is that w dot x is only decreasing as you rotate the cycle, and if you found a minimizer, you have decreased it maximally. You cannot decrease it anymore, right? And how do we find such a weight vector x? Not hard at all, it turns out. Not hard at all. In fact, the weight vector can be 0, 1. How? You take this cycle, we have already given a fixed direction of rotation, and that gives us an orientation on the cycle, E1, E2 through Ek, K being even. If we ensure that this alternating sum, E1 minus E2, etc., is less than 0, then that will happen. Then w dot x going in that direction will only decrease w dot x. And this is easy to satisfy with 0, 0, 1 weights, because we make all of these 0 except one of these negative ones to be 1. And now this we do independently over each walk. For each walk, we label its edges 0, 1, and we got a weight vector for all the weights.
Sorry, that should be true for every cycle.
Yeah, every walk.
So the cycles are edge disjoint.
Cycles are edge disjoint.
Oh, okay, good.
Right. So you found this weight vector which is 0, 1, and you find, and now you are left with the problem of finding the minimizer of w dot x. We found w in parallel. How do we find the minimizer of w dot x? Here we appeal to the fact that we can count the number of perfect matchings, and this time we can actually apply more machinery of counting. Namely, we go with the tut matrix, and here we put down t to be a variable, and normally you would have put 1 minus 1, but here you put t to the weight we and minus t to the we. We's are plus minus 1, so everything is easy. And then if you had a Pfaffian orientation, then look at the minimum the minimum power of t, minimum degree monomial that survives, t raised to some alpha. That alpha will be 2 times the weight of the minimum weight perfect matching, right? So compute this polynomial, look at the minimum minimum degree monomial that survives. If that degree is alpha, then alpha over 2 is the weight of a minimum weight perfect matching according to this weight vector w. And so we can compute and its coefficient will be the square of the number of minimum weight perfect matchings. So you can compute the minimum weight number of minimum weight perfect matchings. You can also compute the minimum weight perfect matchings containing E, and so their ratio will be this minimizer of w dot x on that face. Okay. So we are there where we have killed every cycle. Every cycle got blocked. Okay. And now what do we want to do? Every cycle got blocked because of one of 2 things. Either it lost an edge, which is a happy state, easy state, because we remove that edge when we have a smaller graph, or it's because it got blocked by a tight offset. And that tight offset we have to find, like to answer your question, right? So if this cycle is blocked because of a tight odd set, we must find that tight odd set. How do we find that? Well, so that comes to the second idea here. How do we find these tight odd sets?
So do you also care about the size of this odd set? It
No.
could be, why can't it be that many?
It could be many cycles are on the same tight odd set.
So then you're not making enough progress, right?
But then that shrinking that tight odd set will shrink at least one edge from each cycle. So the number of edges shrunk. If you shrink all the tight odd sets, the number of edges shrunk is
So
the number of cycles.
set block many cycles and it must be big.
Yeah,
So
it must be
have
big and
odd
it must shrink all those one edge for each cycle. Right?
So the shrinking process must recurs, right?
We'll come to that. Yeah, good idea. Good questions. Yeah, nice question. Yeah. So let's keep assume that we don't go too far into the thought process. Just enough, right? So for now, let's just say that we want to find this tight odd set that is blocking one cycle. It may be blocking many other cycles also, but the one that's blocking this one cycle. Okay. So how do we find this tight odd set? So here's what we do. So let's say there was some cycle here, and it's being blocked by this tight odd set. If we rotate this cycle a bit more, just by a small epsilon, then this tight odd set, or one tight odd set, will go under tight. It will be infeasible. And in fact, it will be one of these, which is blocking this cycle, will be a minimum odd cut in the graph. There is nothing smaller. There are no smaller odd. Every odd cut is at least one, including singletons. So if we did a small rotation along that, this goes under 1, and if we pick out the minimum odd cut, that will give us a tight odd cut. Okay? Why will it give us a tight odd cut? Or rather, how will we get that tight odd cut? Still, right? We don't want to do this binary search thing, right? So there's a beautiful theorem of Padberg and Rao in the context of matching that says that among the GammaU cuts, there is one that is the minimum odd cut in the graph. Okay, so you know that every undirected weighted graph has a tree incident at it, which is called the GammaU tree. Okay, how many people don't know GammaU trees? Because I'll define it, and oh really? Okay. Huh? Okay. So what is a GammaU tree? So you take any two vertices S and T, okay, and between S and T there's exactly one edge, one path in the tree, right? Let's say this path. The edges of the GammaU tree also have weights on them that come from the GammaU procedure. And look at the weights of the edges on this path from S to T. Pick the minimum weight. Okay, that will be the minimum cut between S and T in the whole graph. And if you remove that minimum weight edge, you have disconnected the tree into two components. Look at that cut as S complement. So the vertices of the two subtrees. Okay, that will be a minimum ST cut in the whole graph. Okay, so now one of these n-1 cuts will be a minimum odd cut in the given graph, and so we can find it because we can compute ST minimum flows in parallel due to an ancient algorithm of Johnson. This is not David Johnson. This is the other Johnson, and using that we can compute a GammaU tree in NC. Okay, so therefore we can get all the odd tight sets because for each cycle that didn't lose an edge, it's blocked, and we can in parallel get all the tight odd sets. Some of them may be the same if two cycles share the same odd set. Okay, but we cannot shrink all these tight odd sets because they can cross arbitrarily. Okay, we have to uncross them first. I mean, if two sets cross, yes, you can shrink this, but you cannot shrink both. So we have to uncross them, and you know, uncrossing is a very sequential process. So what we do is what we're interested in is not the entire uncrossing, but the outermost sets. Like here, the uncrossing would be S intersection T and S union T. We don't care about S intersection T, because if we got S union T, shrink it, the other thing is also shrunk inside. So we want the outermost sets in the uncrossing, and we have a divide and conquer approach. So we take the first M over 2 sets, uncross them to get these outermost sets P's, and the next to get the Q's. And now we want to do a merge, which is where the whole algorithmic idea lies. So how do we merge the P's with the Q's? Well, we first make this graph where we put an edge. So the P's are all disjoint. They are the outermost sets. The Q's are all disjoint. They are outermost sets. Put an edge between a P and a Q if their intersection is odd. And then you'll have a connected graph, or you take every connected component and try to deal with it separately. And then first question that arises is, can you just shrink all the P's and the Q's? Is that an odd tight set? When is that an outside tight set? Well, first of all, this parity graph must be connected. Secondly, the parity of the number of vertices inside this union must be odd, which happens to be easy to compute. And if that's the case, then in fact you can show that this entire union is a tight odd set. If not, then we can show that you can partition these, or rather you can find two subsets which are both tight odd, and they involve all the P's and the Q's. So that can be done, okay? So the uncrossing got done, and at this point we got, say this is the uncrossed picture, right? These are the odd sets that we found. And so we are in one of two cases. Either we managed to remove omega n edges, or we have managed to find outermost tight odd sets that shrink lots of edges. Okay. In the first case, life is easy. Just proceed with the rest of the graph. In the second case, what do? We shrink these outermost tight odd sets and find a perfect matching in the remaining graph. So it will be these edges. On this, we find a perfect matching, which is, because this will be one vertex, this will be one vertex. So this is one perfect matching in the outside. And then we open up the tight odd sets and find perfect matchings inside, recursively, both. Okay? And I can guarantee you that the depth of this recursion is order log n. Okay? But the time of the recursion is not polylog. Anybody see the reason? I mean, it's there over here, but. So the time is not polylog n because, So you want to shrink these, find perfect matching in the shrunk graph, and then recursively, of course, because the shrunk graph may be huge and may have lots more shrinkings to happen. And then you open each of these guys and find perfect matchings in them recursively. Yeah?
The shrunk graphs might have only been a little bit smaller than the original.
It doesn't matter.
Yeah.
It doesn't matter because you have shrunk enough edges altogether. But the point,
you need to know the edge in the tight set before.
Good. So you need to know these edges before you can find the matching inside. So there's a sequentiality here, and this sequentiality and the fact that both of these are recursive calls, once you write out with those two constraints, when you write out the recursion, it'll turn out to be not polylog time anymore. Okay. And at this point, it looks like, we are back to square one, right, after all this work. But fortunately not, just needs one more idea. Namely, why not find a balanced tight odd set? Okay, meaning a tight odd set which has omega n vertices inside and omega n vertices outside. Because any edge that is in this tight odd set can be matched in one time unit, and then you can go and find matchings in both of these halves already, and you never needed a recursive call there, right? So if you can find it now, why couldn't we find it earlier, this balanced tight-out set? Turns out all of those ideas are needed to find this balanced tight-out set. Okay, so we find the balanced tight-out set and move on. So basically, it involves lots of shrinkings until we have a constant size graph, and then we find a balanced tight-out set and find a match an edge on it, and then break the problem into two without any recursions at this point. Okay, and then continue recursively inside. And that's it. So we got a planar graph perfect matching algorithm, and in fact, it extends to minimum weight perfect matching also. Then we can also do constant genus graphs. And I mentioned this work where I had given an algorithm for finding the number of perfect matchings in a K33 free graph. And actually, at that point in '88, I had asked whether, because of that counting being in NC, can you also find the matching in NC? And so this is the next problem that had to be attacked. And together with David Epstein, my colleague at UC Irvine, we managed to show this not only for K33 free graphs, but any one crossing minor free graph. So take any graph H, which has one, whose planar embedding has only one edge crossing, like K33 or K5. So take any H minor free graph, this class for a given H, all the graphs that don't contain H as a minor, and then over all H's. And in all these graphs, you can find not just a minimum weight perfect matching, but also, not only the perfect matching, but also minimum weight perfect matching for polynomial weights. And of course, at this point, we have more or less come to the end of this era of beautiful progress, because so far, we had one of two amazing, amazingly powerful algorithmic, how do I call it, like tools or whatever to help us, either randomization or an oracle for counting the number of perfect matchings. Okay, very powerful, both of them. And now, if you don't have randomization and you cannot count, because in bipartite or general graph you cannot count, you're left without all these supporting structures, and you're out in the open, really, the wild open. And I don't know what will work here. I really don't know. It's a very hard question. Yeah, so all the support structure is gone. This is the end of probably the road of support structure, probably. Unless somebody wants to do minor closed families or some such thing, which may be doable, but with a lot of effort. But how to go further is now a very, very big open question. And this is really is matching in NC is really a Mount Everest of one of our Mount Everests for theoretical computer science. And it is easy to believe that whatever comes out as an algorithm will come also with big ideas that we can use for other problems or for the whole field. That's always been the case with matching. So that's why it's so important to do it. Yeah, thank you. Yeah. Sorry?
I lost track of where you actually use planarity. One point where you use
3 points.
Okay, so
Counting.
So the counting you use to find a fractional matching which is inside the polytope.
So counting, and then the
number of edges.
No, wait a minute.
Just
The number of disjoint cycles.
Yeah.
And the max ST flow, which gave us the GammaU trees in NC.
So yeah, okay. So regarding that last point, then why using ST flow you can also find bipartite matchings, bipartite planar.
But we are not in bipartite.
Yeah, but you also cited some other result which was.
You can do bipartite.
Okay.
Perfect
anyway,
matching.
So okay. So anyway, so the second question was
No, as soon as you take a planar graph and put S and T and connect to all this side and this side, you may not have planarity anymore. That's the reason they do it through some multi-commodity flow in planar graphs. Yeah.
Just a reminder, even for things in P, what's the kind of largest class of graphs which we know how to count? Is that,
These are it.
this is it?
Whatever you can do with Pfaffians.
Okay.
I don't know any other way of counting. Yeah. Yeah.
Just to make sure I understood what was happening, so
Sorry, I'm sorry. Sorry.
Just one.
I was wrong completely. So this class then. Here you go further. You basically do some decompositions, and then you reduce it to those Pfaffian things and patch it all together. So yeah. Sorry.
Because your one crossing minor free also is covered in that a little more generally, right? Or can you not count those?
Then you can count those.
Yeah, okay.
You can count those.
But you're counting in NC, and I was wondering whether there was anything.
So whatever.
all of them
are
are
NC.
reduced to Pfaffians at the
Yeah.
level, and so then they're going to be NC if they're going to be free.
Seems like, as far as I can tell, as far as I know, anything that can be counted in P can also be counted in NC so far. So, but you may prove me wrong by some result that I'm not aware of. I don't know. Yeah.
so I was just wondering, so at some point there's this weight minimizing step, and that's done by calculating the Pfaffian
Yes.
and I guess differentiating it or something.
No need to differentiate it.
Or
Just compute
as a polynomial, like
that polynomial, the determinant.
so you can
Has
even
only-
calculate a polynomial expression efficiently.
Yeah, because the degrees are small.
Okay, I see.
It's a one variable t
Yeah.
raised to a small power, so you can
Uh,
compute the determinant.
I see. Well, isn't it like a polynomial power, or I don't.
Right. You will get a polynomial as a
That's-
determinant, but it will have very, very few terms, and you can compute it in NC also.
Okay, I guess. So I was wondering, like.
So there's a very nice paper of Borodin, Cook, and Pippinger that shows how to do that in NC. That goes a little bit beyond Shankly.
So I was also wondering, so like in principle, if you just like found a good weight, could you just like for example, I'm not sure if you can do this, but like if I picked a random weight, then probably the minimizer will be like an actual perfect match, right?
So if you apply the isolating lemma, then minimum weight perfect matching will be unique, and that's how you normally would pick it out if you had randomization, but we don't. Yeah. Any other
Yes.
questions, or we are all done,
So
or we can
we're
take it later?
Over time, so let's
Yeah.
stop here.
So
and
thank
take
you
our
all.
questions
Yeah.
offline.